All right, we're about to dive into a part of computer science that honestly secretly runs just about everything. It's called automata theory. It's all about these abstract little machines, and you are about to see how they connect some of the most random sounding things you can imagine, from spell checkers to the entire universe.
So let's start with a puzzle. What on earth could possibly connect the software on your computer, the patterns you see in nature, like a pine cone, and, the very fabric of reality itself? I know, it sounds kind of out there, but the answer is actually really cool. So the key to that whole puzzle? Well, it starts with an idea that goes way, way back, all the way to ancient Greece, with this concept of a self-acting machine.
And the answer is automata. The word literally comes from Greek, and it just means self-acting or self-moving. You can just think of them as simple, abstract little engines that follow a pre-written set of instructions, completely on their own. They're basically the foundational building blocks for how we think about computation.
Okay, so how do these machines actually think? Well, it's not really about thinking in the way we do. It's more about following a very simple set of rules with absolute, perfect precision.
So here's the whole idea in a nutshell. An automaton is just this abstract little device that automatically follows a sequence of operations. It takes in some information, an input, it follows a rule, and it changes its state. That's it. Sounds simple, right? But it is incredibly powerful.
A really good way to picture this is to think about a simple electronic lock. The lock doesn't need to know your whole life story or remember every code you've ever tried. Nope, it only needs to know two things. What's its current state? Is it locked or unlocked? And what input did it just get? What number did you just punch in?
So every one of these machines, or what we call a finite state machine, really just boils down to these three things. First, you have states. That's where the machine is right now, like locked. Then you have inputs. That's the info it gets, like a 1 or a 0. And finally, you have transitions, which are just the rules, those arrows that say, hey, if you're in this state and you see this input, you've got to move to that state.
All right, let's watch one in action. Say we give it the input 0, 0. Follow along here. We start in state S1. It reads the first 0, and that arrow tells it to move to state S2. Okay, now it reads the second 0, and that arrow sends it right back to where it started, state S1. And since that's the end of our input, that's where we stop.
So why does that matter? Well, do you see that double circle around S1? That's the key. That means it's an accepting state. And because our little journey ended there, the machine has officially recognized 0, 0 as a valid sequence. This particular machine is actually built to recognize any sequence that has an even number of zeros. And in the world of automata theory, that collection of valid patterns is what we call a language.
Now, that simple little machine we just saw, that's just the beginning. It turns out, if you add just one new feature, you can create a whole ladder, a hierarchy of way more powerful machines. And that one single game-changing feature is memory. The machine we just looked at has zero memory of the past. It only knows what state it's in right now. But the second you give a machine a way to remember things, oh man, its abilities just explode. And that brings us to this, a simplified version of what's called the Chomsky hierarchy. Down at the bottom, you have our friend the finite automaton. No memory, great for simple patterns, or regular languages. Think of it like a find feature in a text document. But then you add a basic memory, a stack, and now you've got a push-down automaton. It can handle more complex stuff, like making sure all the parentheses in your code match up. And then at the very top, you have the Turing machine, with its infinite memory tape. Let's really nail this down. The finite automaton is totally memoryless. But the push-down automaton, it can use its stack. Just picture a stack of plates to remember things. So when it sees an opening parentheses in a line of code, it can push a little reminder onto the stack. And when it sees the closing one, it can pop it off. That's how it checks if everything is balanced, something the simpler machine could never, ever do. And this whole progression, this climb up the ladder of power, it all leads to the big one, the Turing machine. Now, this isn't a real physical device. It's a theoretical model, a concept that basically defines the absolute limits of what any computer can possibly calculate. It is, in essence, the blueprint for all of modern computing.
Okay, so I know this might all seem super abstract, right? Just computer science theory. But here's the wild part. These ideas, these machines, they are literally all around us. And not just in our technology, but in the natural world too.
I mean, sure, finite automata are the backbone of things like your spell checker and the compilers that build software.
More complex versions are critical for AI and designing computer chips. But then you look deeper. You see things like cellular automata, like Conway's famous game of life, that create incredible complexity from simple rules. And get this, we even see these principles in biology, guiding the growth patterns on seashell, the perfect spirals in a pine cone, and even the spotted and striped patterns on animal fur. It's amazing.
And you know, this isn't some brand new concept. The whole field really took shape back in 1956 with the publication of a book called Automata Studies. It featured papers from absolute giants of the field, pioneers like Claude Shannon and John von Neumann. It's what really cemented automata theory as like the pure mathematics of computer science.
And all of this brings us to a really, truly mind-bending idea. It's a question that some very serious scientists have actually thought about. What if this isn't just a useful model for our computers and for pine cones? What if it's a model for everything?
Yeah, this is the ultimate leap. This is where we take the theory to its absolute extreme. Could the universe itself just be one giant self-acting machine, computing its own existence from one moment to the next?
And that's the final thought I really want to leave you with. Think about it. If the laws of physics are just the transition rules, and the state of the universe right now completely determines the state of the universe in the next instant, well, does that mean we're all just living inside a vast computation? Is reality itself just running a program?